In section 1.8, we continue working with methods of solving quadratic equations that cannot be factored. In our last section, we worked on completing the square, and in this section, we'll be working on using the quadratic formula. Also, we'll look at how we can use a portion of the quadratic formula, the discriminant, to predict quantity and types of solutions. So key vocabulary here is the quadratic formula and the discriminant, which is a portion of the quadratic formula. So the quadratic formula is x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And remembering the a, b, and c come from standard form of the quadratic function, ax squared plus bx plus c. So this is where we get the a, b, and c. We plug them into these locations and simplify. Okay, now the discriminant is a portion of this. It's the portion that is here in the radical, so it is actually the radicand from the quadratic formula. So it's b squared minus 4 times a times c. And taking a look at this will allow us to predict quantity and types of solutions. And when you really think about the idea that this is what's inside a radical, it will all sort of make sense as we talk about it. Again, talking about problems that we might solve using the quadratic formula or modeling with a quadratic function. Here's a problem about throwing an object into the air. So we're talking about a juggler who's going to toss a ball in the air. The ball leaves the juggler's hand 4 feet above the ground, has an initial velocity of 40 feet per second. The juggler catches the ball when it gets back down to 3 feet, so a foot lower than where he threw it from. How long does it take for the ball to make that journey? So when we get to the end of this section, we'll go through solving this problem. Before we get there, let's take a look at some of these ideas. So here again is the quadratic formula. Right? We're still looking at standard form of a quadratic in order to identify our a, our b, and our c, and then we would plug them into this formula. So in this case, I have this equation. A is equal to 1. I have 1t squared. B is equal to 8. I have 8 times t to the first power. And c is equal to 19. So when I plug those in here, I have the opposite of b, so the opposite of 8, plus or minus the square root of b squared, which is 64, minus 4 times a, which is 1, times c, which is 19. And it's all going to be over 2 times a, which is 1. When I simplify this, I'll have the opposite of 8 plus and minus the square root of 64 minus, well, 4 times 1 is 4, 4 times 19 is 40 plus 36, that's minus 76 all over 2. Simplifying the radical, minus 8 plus or minus 64 minus 76 would be negative 12 all over 2. This is an 8. I swear this is an 8. Okay, so I would now want to look at simplifying my radical, and I'm also going to do a step that is distributing the division. If I have an item plus or minus another item and they're all being divided by a number, I can distribute division in the same way that we distribute multiplication. So I'll have negative 8 over 2 plus or minus, the sign doesn't change, the square root of negative 12. Well, I want to factor out the negative 1, so negative 1. I'm going to factor out a perfect square, which is 4, and I'm going to have the remainders, which is 3, and all of this is over 2. As I continue to simplify, negative 8 divided by 2 is negative 4. Plus or minus, this is going to be 2i radical 3 over 2, and this 2 will cancel with that 2. So my final solution here is x is equal to negative 4 plus or minus I root 3. And that's how we simplified. So predictably, when the radicand, this will add up to some information we'll talk about later, when the radicand here became a negative number, I ended up with imaginary solutions, because as soon as I start taking the square root of a negative number, my solutions are imaginary numbers. Okay? Here's another example. Now the difference here is we're not in standard form. You see 15 is on the other side of the equation, so before I can identify a, b, and c, I have to move 15 to where it belongs. So x squared plus 6x plus 15 equals 0. Now I'm ready to identify a, b, and c. A is 1, b is 6, and c is 15. So when I plug those in, I'll have x is equal to the opposite of b. I'm sorry, this is 6. The opposite of 6 plus or minus the square root of 6 squared, which is 36, minus 4 times a times c, all over 2 times a. So I'm going to go ahead and I'm going to not go as slow as I did in the last example. I'm going to go ahead and distribute the division now and do some simplifying of the radical. So I'll have negative 6 over 2 plus or minus the square root of 36. 4 times 1 times 15 is 60. 36 minus 60 is 24. So it's going to be negative 24 over 2. And if we continue to simplify, negative 6 divided by 2 is negative 3, plus or minus, and this will be the square root of negative 1 times the square root of 4 times the square root of 6, all over 2. Okay, so we'll have negative 3 plus or minus, the square root of 4 is 2, square root of negative 1 is I, root 6 is sort of a remainder, all divided by 2, and these will cancel. So my solution is negative 3 plus or minus I root 6. You'll notice that the solutions that we're getting here are very similar to the solutions that we were getting from completing the square. That's really typical because they were non-factorable quadratics. The answers end up looking something like this: complex numbers, or a number plus and minus a radical, or sometimes they work out to be integers, but not very often. Okay, so when we're talking about the discriminant, we just did 2 examples where the discriminant came out to be negative. In both cases, my solutions were in the realm of imaginary numbers. And that makes sense because the discriminant is in a radical. So if I take the square root of a negative number, I'm going to have 2 imaginary solutions. So this is when b squared minus 4ac is less than 0, like our 2 previous examples. You saw I got 2 imaginary solutions. Typically, when b squared minus 4ac is greater than 0, not even typically, always, I'll end up with 2 real solutions because I'll have a real number plus and minus another real number. So plus the real number would be one solution, and minus the real number would be another solution. And when b squared minus 4ac equals 0, then, as the book says, I'll have one real solution, but what I actually believe is we'll have one repeated solution. So I'll have the number plus and minus 0. So plus 0 and minus 0 will give me the same result, but it really still ends up being 2 solutions. That will make a lot more sense when we move into chapter 2 and we're counting how many solutions we're solving. We count repeated solutions as more than one solution. So even though the value is the same, so there's one real value that is a solution, that solution occurs more than one time. Okay, and I know that might seem like a weird idea, but we'll work with it later. Okay, so some more practice in going through these problems. A is equal to 3, B is equal to negative 8, C is equal to negative 9. If I go through to solve, I'm not going to just classify, I'll classify it as we go along. So if I want to know what type of solutions we'd have, I take b squared, right? So I'll have negative 8 squared minus 4 times a, which is 3, times c, which is negative 9. So I'll have 64 minus 4 times 3, right, but minus a negative number, so it's going to be 36 times 3, so I multiplied the 4 times the 9 to get 36, times 3. 3 times 36 is 90 plus 18, so that's 108. So it would be minus negative 108. That ends up being plus. So I know I'm going to have two real solutions. 64 plus 108 is 172. Now I could go ahead and just put that right into the quadratic formula because I've already simplified the b squared minus 4ac part. So I'll have the opposite of b, the opposite of negative 8 is 8, plus or minus this part that I've already done here, over 2 times a, which is 3. And now I'd want to simplify 172, so I'm not sure about perfect squares in 172, so let me go ahead and start doing a factor tree. 8 and 12, so that would be 86, and half of that would be 43, and that looks like about as far as we're going to go. So I'm going to be able to factor out a 4. So I'll have 8 plus or minus, right, when I go ahead and, this would be the square root of 4, which will simplify to be 2, root 43. So you see when I have a pair, that number comes out, and this number stays in the radical. All over 6. So I'll have 8 over 6 plus or minus 2 root 43 over 6. This simplifies to be 4/3, and this simplifies to be root 43 over 3. And there's my solution. Continuing on with this problem, this one's a little different in that it's not in standard form, so I'd like to put it in standard form. And if I have the option, I'd normally like my leading coefficient to be positive, so I'm going to move all of these guys to the other side. So I'm going to add, it's going to end up equaling 0, so I'm going to add 5v squared, and I'll get 5v squared. I'm going to add 8v, 8v plus 2v is 10v, and I'm going to subtract 3. When I go ahead and go through now and plug this into the quadratic formula, I'm going to have the opposite of 10 plus or minus the square root of 10 squared, which is 100, minus 4 times a times c. Right? And you notice every time if c is a negative number or if a is a negative number, it's going to be minus a negative, which is, you know, it's going to come out to have real solutions like this one. All over 2 times a. So I'll have negative 10 over 10 plus or minus. So this is going to be 100, and it's going to be plus 60. 4 times 5 is 20, times 3 is negative 60. So 100 minus negative 60 is 160. All over 10. Right, so I know I can see that 16 is a factor here, so I'm going to factor the 16 out and leave a 10 in. Negative 10 divided by 10 is negative 1, plus or minus, right? Square root of 16, which is 4, root 10 over 10, and I know that I can factor a 2 out of this and out of this, and I end up with negative 1 plus or minus 2 root 10 over 5. So a couple more examples. Again, we're working out of what would be our typical form. So the first thing we want to do is we want to start getting things all sort of put together into standard form. So what I'm going to do here is I'm going to set this side to be equal to 0. I'm going to get all my like terms combined on the other side. So I know this side's going to equal 0. I'm going to add 3x squared to either side. So 3x squared plus 2x squared is 5x squared. I'm going to subtract 7x, so I'll have 2x minus 7x, that's minus 5x, and then I'll have plus 85. So I've got all of my like terms combined, and you can see that 5 will go into each of these terms. So I'm also going to factor a 5 out. That's going to help make all of my numbers smaller. So I'll have x squared minus x, and 5 goes into 85 like 17 times. Okay, so now this is what I'm going to work with in the quadratic formula. So I know that A is equal to 1, B is equal to -1, and C is equal to 17. I would get the same solutions if I worked with 5, -5, and 85, but you can see it's going to be a lot easier to work with 1, -1, and 17. So x will be equal to the opposite of b, so the opposite of -1 is 1, plus and minus the square root of -1 squared, which is 1, minus 4 times a times c, all over 2 times a. And as I simplify, I'll have 1 plus and minus the square root of 1 minus 4 times 17 is 40 plus 28, that's 68. All over, sorry, 2a, I wrote 2a up here, but a is 1, so this would be over 2. So I'll have 1 plus and minus the square root of -67 over 2. So when I finally simplify, this is going to be 1/2 plus and minus I root 67 over 2. Okay, so this is my solution right here. All right, one more example here. Now this is, it looks almost like it's in vertex form, and yet it's really not. So I'm going to square the binomial, multiply it by 4, and then combine like terms. Then I'll be able to set about solving. So this is going to be 4 times x squared minus 2x plus 1, and that will be equal to 6x plus 2. And I got this by foiling this. Okay, so I happen to use the special pattern, which I know. A minus b squared is equal to a squared minus 2 times a times b, so 2 times x times 1 gives me 2x, plus b squared, -1 squared is 1. So I'll get 4x squared minus 8x plus 4. And now I can set about combining like terms. I'll have 4x squared minus 14x plus 2 is equal to 0. So I subtracted 6x and I subtracted 2. Again, you can see that I can factor a 2 out of everything. So I'll have 2x squared minus 7x plus 1. Again, it doesn't impact the answer. What it does is it makes the numbers that I work with smaller, and it reduces the amount of simplifying I have to do at the end. If I don't notice that I could factor a 2 out of this, or in this case, if I didn't notice that I could factor a 5 out, it won't change the end result, but it will make the problem just a little bit more difficult. Okay, so here a is equal to 2, b is equal to -7, and c is equal to 1. And when I plug them into the quadratic formula, I'll have the opposite of -7, which is 7, plus or minus the square root of -7 squared, which is 49, minus 4 times a, which is 2, times c, which is 1, all over 2 times a, which is 2. So I'll have 7 plus or minus the square root of 49 minus 8 is 41 over 4. And that will simplify to be 7/4 plus or minus. I'm trying to think of what can go into 41. I don't think it's really divisible by anything. So I'm going to go ahead and leave that. If I made a mistake, you let me know. This would be my final answer, 7/4 plus or minus root 41 over 4. So now we're going to go back to the problem we started with, which was the problem of the juggler, and we're going to talk about this concept of modeling launched objects. Now, we have 2 formulas here, and I'm going to put it to you that we really don't need 2. We really just need this one. Okay, the thing that's important to understand is that while they've created a formula for an object being dropped and a separate one for an object being launched or thrown, when I'm simply dropping an object, its initial velocity is 0. So when you plug 0 in for v, in this formula, you'll see that it just becomes that other formula. So if you're going to memorize a formula, this is the one to memorize because it works for all circumstances. Okay, this one is only for an object being dropped. It assumes an initial velocity of 0. Whereas if you use this one, like I said before, with an initial velocity of 0, it simply reverts to being this other formula. So you don't really need two. Okay, the concept of velocity is that velocity has directionality. So you see, in this case, the fellow hitting a golf ball, he's driving the golf ball up, so my velocity is positive. In the case of the volleyball player, he's striking the ball downward, so my velocity would be negative. And if you're launching off flat, or if you're dropping it, my velocity would be 0. So as you read a problem, what you need to think about is, if it's talking about the velocity, the starting velocity of the object, you need to think about, is it going up, is it going down, or is it moving horizontally, before you start applying a value to initial velocity. Okay, so in our case, a juggler tosses a ball into the air. So he's tossing the ball up, velocity, initial velocity. The reason they use a subscript of 0, that means at time 0. Initial velocity is going to be greater than 0. So the ball leaves the juggler's hand 4 feet above the ground. Okay, so that's going to be height, initial height. So height at time 0, right when it lets go of it, it's 4 feet off the ground, has initial vertical velocity of 40 feet per second. So initial velocity is 40 feet per second. Juggler catches the ball when it falls back to a height of 3 feet. So that's the height at the end. How long is the ball in the air? We're looking for t. The height at time t is equal to 3. That's our ending situation. If I take these values now and I plug them in, I'll have 3 feet. The height at the time I'm looking for, at the very end when it's back in his hand, is equal to negative 16 t squared. Remember, that's gravity, plus the initial velocity, 40 feet per second, times time, plus the initial height of 4 feet. To solve, I want to subtract 3 from either side. So I'll end up with negative 16t squared plus 40t plus 1. 4 minus 3 is 1. The key element also when we're talking about units of measure, you want to make sure that the velocity is in distance, right? Velocity is going to be distance related to time. You have to make sure that the time is the same time that we're using here. In this case, it is seconds. This is seconds, so we're okay. Otherwise, I'd have to convert this velocity. So that's just something to watch out for. If I want to solve this, x will be equal to negative 40 plus or minus the square root of 40 squared, which is 1600, minus 4 times a, which is negative 16, times c, which is 1, all over 2 times a, which is negative 16. So when you think about this and the values I've got, the plus and minus thing now feels very strange, because how could I have two different answers for time from the juggler throwing the ball up in the air and then catching it? How could I have two different times? And as you see, when the times work out, it will all sort of make some sort of logical sense to you. So when I simplify, I'll have negative 40 plus or minus the square root of 1600 minus negative 64. So that's 1664 all over negative 32. Now 1664 is, square root of 1664 is just a little bit over 40. Okay, so that's going to be negative 40 plus or minus, I'm going to use a decimal, so it's 40.79 all over negative 32. So when you think about the different answers I might get out of this, and I will get to, when I add 40.79 to negative 40, I'll get 0.79 over negative 32. Wow, okay, this is a very small value, and it's also negative. So what you need to think about in time, if I have a negative measure of time, that means it's before the problem begins. If it's less than 0, it's actually before the juggler throws the ball in the air. So is it possible for him to throw the ball in the air and for it to land back in his hand in the past? This is not a possible solution. Okay, it's actually related to something else, which might be interesting in another problem, not possible. So if, on the other hand, I subtract 40.79, I'll get negative 80.79 over negative 32. This will give me a positive solution, and it ends up being approximately 2.5 seconds. Okay, that's more logical. Obviously, it's not going to end in the past. When you think about the juggler, and you may already know that I draw poorly, so if the juggler throws the ball, right, he's going to throw the ball into the air, and it's going to land in his other hand. So we have an axis of symmetry on this that's going to pass through here. If we found the vertex, we know the maximum height. That would be interesting. But we're finding, where did it land here? So now the question is, what's this negative value? The negative value would be if the ball had been, instead of tossed from his hand, if it had been launched from the ground, it would have happened, it would have gone from the ground. Because remember, we're going to get two different solutions, right? And actually, since our solutions are here at 4, it's actually, or actually at the 3-foot mark, right? This is 3 feet where the ball lands back in his hand. So if the ball had been launched from 3 feet instead of from his hand at 4 feet, it would have had to have been launched 0.79 divided by 32 before our start time. So just know that if you have time that's negative, it's in the past, that's not possible. So that shows you which answer you should select.